Deep under the cold waters of the Pacific Ocean, right off the west coast of North America, a massive piece of the Earth is stuck tight and bending like a giant wooden board. The ocean floor is shoving itself underneath the land at this very moment, but the heavy rock refuses to slide smoothly. Massive amounts of energy are piling up in total silence right now, straining the planet until something finally breaks. The rock cannot bend forever, and every single second brings us closer to a sudden, violent snap. If you love exploring the real mysteries of our living planet without any fake hype, make sure to hit that subscribe button right now. We dig deep into real scientific discoveries every single week, so you can be the very first to know what is actually happening beneath our feet. To understand why scientists are so deeply worried today, we have to look back at a mysterious puzzle that took over 2 centuries to solve. For a very long time, people living along the Pacific Northwest coast in Washington, Oregon, and Northern California believed their coastline was peaceful and safe from massive earthquakes. California had famous shaky faults like the San Andreas, but the coastal waters further north seemed strangely calm. Local towns were built right along the water. Roads were laid out next to beaches, and huge cities grew without anyone realizing the massive dangers sleeping just offshore. For more than 100 years, geologists assumed that the Pacific Northwest was simply a quiet region where the tectonic plates under the sea slid past each other without causing any trouble. They looked at the historical records left behind by European settlers in the 1800s and found no reports of huge earthquakes along the coast. Because there were no written records of giant tremors, people naturally believed that the region was naturally immune to devastating seismic events. Buildings were constructed without any special earthquake reinforcements, and major ports were constructed right on soft, sandy shores. However, if you paid attention to the local landscape, strange clues were hidden in plain sight along the estuaries and river mouths of Washington and Oregon. Mysterious groups of dead western red cedar trees stood bleached and barkless, sticking out of the salty tidal mud like giant gray fingers. These strange collections of dead trunks were known locally as ghost forests. For decades, locals and visiting tourists wondered what could have killed thousands of huge, healthy trees all at once across hundreds of miles of coastline. Some people thought a massive disease had swept through the forest, while others believed a sudden change in global climate had poisoned the soil with salt water over many years. But neither of those theories could explain why the trees died at the exact same time in completely different river valleys, separated by long distances. The ghost forests remained an unsolved nature mystery for generations, standing as silent sentinels watching over the Pacific coastline. At the same time, native people who had lived in the region for thousands of years held rich oral histories that told a very different story about the land. Stories passed down through generations of the Maka, Hu-Ayat, and Quinault tribes spoke of a terrifying night long ago when the ground shook so violently that people could not stand on their feet. According to these ancient legends, the shaking was followed by a massive wall of ocean water that swept inland, destroying entire villages on Pachena Bay and washing away canoes tied high in the trees. Scientists in the middle of the 20th century often overlooked these native stories because they were searching for written records and hard physical proof. But in science, natural clues are always waiting for someone with the right tools to come along and read them. The mystery of the ghost forests was about to be unraveled by a determined researcher who decided to look beneath the surface of the coastal mud. In the middle 1980s, a young paleogeologist named Brian Atwater set out to solve the puzzle once and for all. He hiked deep into the muddy tidal marshes along Nia Bay and the Salmon River in Washington state, carrying a simple hand tool called a soil corer. He pushed long hollow metal tubes into the wet marsh dirt and pulled up long vertical cross-sections of the earth beneath the grass. What he found inside those dirt samples completely revolutionized our understanding of West Coast geology. When Atwater examined the soil layers, he saw a clear and disturbing pattern trapped in the earth like pages of a history book. Near the bottom was a thick layer of dark, rich marsh soil containing preserved roots of ancient freshwater plants. Sitting directly on top of that marsh soil was a thin layer of ocean sand, and resting on top of the sand was a heavy sheet of dark marine bay mud. This proved beyond any doubt that the freshwater marsh had not slowly drowned over decades. It had dropped several feet below sea level in a single catastrophic instant. When the ground suddenly dropped, ocean waves rushed in and covered the fallen marsh with a blanket of sea sand. Salty ocean water flooded the roots of the cedar trees, killing them instantly and preserving their roots in the oxygen-poor mud beneath. This sudden drop of the land is known as coastal subsidence, and it only happens during the largest earthquakes on planet Earth. Atwater had found the physical footprint of a giant megathrust earthquake, proving that the quiet coastline had experienced a massive disaster in the past. Did you know that buried mud layers and dead trees can act like a natural time machine to record giant ancient earthquakes? Drop a comment below if you think it is amazing how geologists solve historical cold cases, and tap that like button if you are enjoying this real science story so far. Even with the mud layers discovered, scientists still faced a major hurdle: They did not know the exact year or time that this giant earthquake had taken place. Tree ring studies on the dead cedar trees showed that the trees had stopped growing right after the summer of 1699, meaning the catastrophe happened during the winter of 1699 or early 1700. But without written local records from that era, pinning down the exact date seemed almost impossible. The final piece of the historical puzzle came from across the ocean in Japan, over 4,500 miles away. Japanese historians had kept detailed written logs of weather, fires, and sea conditions for hundreds of years. In their records from the late Edo period, they documented an extraordinary event on the night of January 27th in the year 1700. A sudden, massive tsunami swept into coastal villages along the main island of Japan, destroying homes, flooding rice paddies, and damaging salt kilns. What puzzled Japanese scholars for centuries was that no local earthquake had been felt anywhere in Japan before the giant waves arrived. In Japanese historical accounts, this event was recorded as an orphan tsunami because it appeared to have no local parent earthquake to create it. For nearly 300 years, the origin of this phantom wave remained a total mystery in Japanese maritime history. In the late 1990s, an international team of seismologists and oceanographers connected the Japanese orphan tsunami records with Brian Atwater's ghost forest data in Washington. Using supercomputer models of ocean wave movement, they calculated how long it would take a giant tsunami wave to travel across the entire Pacific Ocean from North America to Japan. The computer simulations matched the historical Japanese wave arrival times with astonishing precision. The data revealed that, on January 26th in the year 1700, at approximately 9 o'clock in the evening local time, a massive magnitude 9.0 megathrust earthquake ruptured along 600 miles of the Cascadia fault zone. The coastline dropped up to 6 feet in seconds, sending a 30-foot wall of water crashing into North America, while sending a secondary tsunami across the ocean to hit Japan 10 hours later. The gap between expectation and reality showed that the Pacific Northwest was not a safe, quiet zone, but rather a dangerous region that experiences giant megaquakes every few hundred years. To truly understand why subduction zone earthquakes are so incredibly massive, we need to take a close look at the physical engine driving them deep inside the Earth. The outer crust of our planet is not one solid piece. It is broken into large moving slabs called tectonic plates that float on top of hot, semi-liquid rock in the mantle below. These giant plates are constantly moving, driven by heat rising from deep within the core of the planet. Off the Pacific Northwest coast, a small oceanic plate called the Juan de Fuca plate is sliding eastward toward North America. At the same time, the massive continental North American plate is moving slowly toward the southwest. Where these two massive pieces of the Earth collide is called a subduction zone. Because ocean crust is made of dense, heavy basalt rock, it gets pushed underneath the lighter, thicker granite rock of the continent in a continuous process called subduction. The Cascadia subduction zone is a 620-mile-long dipping fault line that runs from northern Vancouver Island in Canada down to Cape Mendocino in northern California. The Juan de Fuca plate sinks down into the mantle at an average rate of about 1.5 inches per year, which is roughly the same speed that human fingernails grow. While 1.5 inches per year might seem slow to us, over 300 years, that motion adds up to nearly 40 feet of physical movement pushed against the continental plate. For a long time, early geologists hoped that subduction zones were smooth, well-lubricated boundaries where the ocean floor could slide downward without getting stuck. If the plates slid past each other smoothly, the movement would only cause small, harmless tremors that humans would barely notice. But modern scientific instruments have shown that the locked subduction zone behaves in the exact opposite way. Eventually, the friction holding the two plates together will reach its breaking point and fail completely. When that threshold is reached, the bent edge of North America will violently snap back toward the ocean, sliding up and over the Juan de Fuca plate by dozens of feet in just a few minutes. That sudden massive movement of rock is what generates a magnitude 9.0 megaquake. Have you ever wondered how much energy is stored inside bent rock miles under the ocean floor? Drop your thoughts in the comments section below, and do not forget to subscribe to our channel to join thousands of curious minds learning real Earth science every week. In recent decades, scientists have deployed advanced space technology to measure exactly how much the North American continent is bending right now. Geodesists have installed hundreds of highly sensitive global positioning system stations all across Washington, Oregon, and Northern California. These GPS instruments are anchored deep into solid bedrock and can track movements of the land as tiny as a single millimeter per year. The satellite measurements have confirmed a stunning and scary reality. The entire Pacific Northwest coastline is physically moving eastward by several millimeters every single year. The land is literally being pushed inland and compressed by the ocean plate, shoving against it from offshore. At the same time, coastal land elevation measurements show that parts of the shoreline are rising upward as the continent bulges under the intense pressure. This continuous deformation is clear visual proof that the subduction zone is fully locked and actively storing elastic energy right now. It is like watching someone slowly pull back a high-powered archer's bowstring further and further. The longer the bowstring is pulled without being released, the more potential energy is stored inside the bow, and the more powerful the release will be when the arrow is finally shot. To understand the difference between earthquakes, we need to compare the Cascadia subduction zone to California's famous San Andreas fault. Many people confuse these two fault lines, but they operate on completely different geological principles. The San Andreas is what geologists call a strike-slip fault, where two continental plates slide horizontally past each other like two cars passing on a narrow two-lane road. Because strike-slip faults only go down a few miles into the crust and involve a smaller surface area, they generally produce earthquakes up to magnitude 7.8 or 8.0. A magnitude 8 quake is certainly dangerous, but megathrust subduction zones like Cascadia involve giant fault surfaces that extend for hundreds of miles under the seafloor. Subduction zones are the only place on Earth capable of producing megaquakes, reaching magnitude 9.0 or even higher. The magnitude scale used to measure earthquakes is logarithmic, which means each whole number increase on the scale represents a massive jump in released energy. A magnitude 9 earthquake does not mean it is just a little bit stronger than a magnitude 8 quake. It actually releases roughly 32 times more energy than a magnitude 8 event. That means a single full margin rupture of the Cascadia fault will release more total seismic energy than dozens of San Andreas earthquakes combined. During a slow slip event, parts of the subduction zone deep beneath the ground slide past each other very slowly over a period of 2 to 3 weeks. The movement is so slow and gradual that no human or animal can feel any shaking on the surface, and no buildings are damaged. It is essentially a completely silent earthquake, occurring 20 to 30 miles underneath our feet. When scientists first discovered these silent, slow slip events, some hoped they were acting as a natural safety valve for the planet. The hope was that by slipping silently every 15 months, the fault was releasing stored pressure gradually, preventing a giant, destructive earthquake from ever happening. But detailed computer modeling soon destroyed that comforting hope and revealed a much darker reality. The slow slip events only happen in the deeper, hotter sections of the fault where the rock is warm enough to stretch and slide like soft wax. Up higher, in the cooler, shallow part of the fault zone near the sea floor, the rock remains completely stuck and locked tight. Every time the deep section slips silently, it pushes extra mechanical stress directly into the locked section right above it, bringing the main fault line even closer to its ultimate breaking point. Do you live in an area where earthquakes happen, or have you ever felt the ground shake under your feet? Share your personal stories in the comments below, and click that subscribe button right now to stay updated on all our deep dive scientific investigations. Now, pay close attention to this next reveal, because a groundbreaking ocean discovery has completely rewritten what emergency planners think about West Coast disaster risks. For decades, scientists studied the Cascadia subduction zone and the San Andreas fault as completely independent geological systems. They assumed that a massive quake on Cascadia would have no effect on California's major faults, and a major strike on the San Andreas would leave when a giant earthquake shakes the continental shelf. It triggers massive underwater mudslides that flow down submarine canyons and spread across the flat ocean floor. These mudflows settle down into distinct sandy layers known as turbidites. By counting and dating the turbidite layers trapped in the mud, scientists can create a precise historical catalog of every major earthquake that has hit the region over thousands of years. Geologists originally expected to find single, clean layers of sand for each isolated historical earthquake event. But when Dr. Goldfinger's team pulled up cores from the boundary region where Cascadia meets the San Andreas, they found something completely unexpected inside the mud samples. Instead of single sand layers, many of the earthquake deposits appeared as distinct double layers, which geologists call turbidite doublets. These doublets consisted of one thick sand layer followed by a thin layer of fine mud, immediately topped by a second distinct sand layer that had formed almost right after the first one. When the research team performed precise radiocarbon dating on the organic material inside the doublets, they uncovered a frightening connection between the two fault lines. The lower sand layer had been triggered by a massive Cascadia subduction quake, while the upper sand layer was created by a separate rupture on the northern San Andreas fault. The physical evidence proved that these two giant fault systems have moved together in rapid succession multiple times throughout history. In several historical cases, the time gap between a Cascadia megaquake and a San Andreas rupture was so small that it could have been mere hours, days, or weeks apart. The discovery proved that a massive earthquake in the Pacific Northwest can act like a falling domino, sending powerful shock waves south through the Earth's crust to trigger the San Andreas fault while it is already under high stress. Instead of having to deal with one regional emergency responders might face a catastrophic double megaquake sequence impacting the entire West Coast from Vancouver down to Los Angeles. Major metropolitan areas, including Seattle, Portland, San Francisco, and Oakland, could experience severe ground shaking in rapid succession. Crucial infrastructure like interstate highways, natural gas pipelines, electrical grids, and fiber optic communication lines that link the West Coast could be severed in multiple locations at the same time. To understand what a magnitude 9.0 Cascadia earthquake will actually feel like on the surface, we have to examine the physics of ground shaking. Small earthquakes produce fast, sharp jolts that last for only 5 to 20 seconds, which can startle people but rarely destroy well-built structures. However, a megathrust earthquake ruptures across a massive fault area hundreds of miles long, which means the shaking process takes a very long time to complete. During a Cascadia megaquake, the ground will shake violently and continuously for 5 to 7 full minutes. Try setting a timer for 5 minutes and imagining your house rolling and bouncing the entire time without stopping. That long duration of shaking causes extreme physical fatigue in building materials, weakening steel beams and cracking reinforced concrete until structures that survive the first minute of shaking finally fail in liquefaction. In coastal river valleys, bays, and filled land around cities like Seattle and Portland, the ground is made of loose, water-saturated sand and silt. When that waterlogged soil is shaken continuously for several minutes, the water pressure inside the soil pores rises until the soil grains lose all contact with each other. While the ground is shaking on land, an even more lethal force is being generated far out at sea. When the locked Cascadia fault snaps, the edge of the North American plate springs upward and seaward by up to 60 feet over hundreds of miles. This sudden displacement of the ocean floor lifts billions of gallons of seawater upward in a fraction of a second, creating a giant series of tsunami waves that spread across the ocean. In deep ocean water, tsunami waves travel at incredible speeds, moving as fast as a commercial jet airplane at over 500 miles per hour. Out in the middle of the ocean, the waves are only a few feet tall and have very long distances between wave crests, so ships passing over them in deep water will barely notice anything happening. But as the waves approach the shallow waters of the continental shelf, they slow down dramatically and compress, growing rapidly in height. Scientists originally thought that coastal residents would have plenty of time to receive emergency phone warnings and evacuate calmly to higher ground. But because the Cascadia subduction zone lies only 70 to 100 miles offshore, the first giant tsunami waves will hit the beaches of Oregon, Washington, and Northern California in just 15 to 20 minutes after the earthquake shaking stops. In many remote coastal towns, official sirens and power lines will be destroyed by the shaking, meaning the violent earth motion itself is the only warning citizens will receive. Do you know how high above sea level your home or workplace sits right now? Share your location elevation in the comments section below, and click the like button if you think every coastal community needs better tsunami defense systems. Now, let us bring the story into the present moment and look at what scientists are observing beneath the Pacific Northwest right now. Researchers are no longer just examining ancient rocks or reading historical Japanese records. They are actively tracking the Cascadia fault zone using the most sophisticated subsea and land monitoring networks ever created. Thousands of broadband seismometers, ocean bottom pressure sensors, fiber optic cables, and hydrophones are sending live scientific data to research centers 24 hours a day, 7 days a week. Every piece of incoming data gathered today confirms that the Cascadia fault is completely locked tight and continuing to store tremendous mechanical strain. The Juan de Fuca plate is still diving under North America at 1.5 inches every year, and the continent is still bending backward under the pressure. It has been 326 years since the last major megathrust earthquake struck the region on January 26th in 1700. The oceanic plate is actually tearing apart deep underground as it forces its way beneath the North American continent. This interior tearing creates new localized fault zones and changes how stress is distributed along the main subduction boundary. While parts of the northern plate are cracking under the pressure, the central and southern locked sections of Cascadia remain under immense stress, holding back enough potential energy to trigger a full margin magnitude 9.0 event at any moment. Even a 15-second warning can save thousands of lives by automatically slowing down high-speed trains, opening fire station doors before power fails, stopping delicate medical surgeries, closing automated gas valves to prevent giant city fires, and giving people time to drop, cover, and hold on under heavy furniture. Technology cannot stop tectonic plates from moving, but smart early warning systems turn knowledge into life-saving action when the ground begins to move. How many seconds of advance warning would you need to drop under a desk if a major earthquake hit your town today? Let us know in the comments below and subscribe to our channel so you never miss out on breaking Earth science stories. When we take a step back and look at the big picture, this is not just a story about ancient mud layers, computer models, and tectonic plates. It is a deeply human story about living on a dynamic, changing planet. For centuries, modern societies built huge cities, long highways, ports, and bridges, with the quiet assumption that the earth beneath their feet was solid, unmoving, and permanent. We built our modern life on top of planet processes that operate on vast geological timescales that dwarf human history. The Cascadia subduction zone serves as a powerful reminder that planet Earth is an active, evolving world governed by physical laws that operate regardless of human plans. Millions of people currently live, work, and raise families in major metropolitan cities like Seattle, Portland, Tacoma, Vancouver, and Victoria, as well as dozens of charming coastal communities along the Pacific Northwest coast. Learning about the real scale of the megaquake danger is not about creating panic or hopelessness. It is about building a safer, more resilient world for the future. By understanding the true history of our planet, engineers can redesign building codes to withstand long rolling earthquake waves, cities can replace old crumbling bridges, and coastal towns can construct tall concrete tsunami evacuation towers to protect residents who cannot reach high hills in time. Knowing that the fault has broken in the past gives humanity the power to prepare, adapt, and build stronger communities before the next big rupture happens. Science gives us the extraordinary ability to read the subtle clues left behind in ghost forests, ocean mud doublets, and satellite signals, allowing us to peek into the future and protect future generations. By respecting the immense power of natural Earth processes and listening to real scientific facts, humanity can continue to live, grow, and thrive safely, even along the edges of our planet's most dangerous megathrust fault lines. If you enjoyed this deep scientific exploration into our planet's hidden mechanics and want to keep uncovering the greatest mysteries of Earth and space with us, make sure to hit that subscribe button right now and turn on all notifications so you never miss a new release. Drop a comment below telling us what surprised you most about the Cascadia Fault, and share this script with a friend who loves real science as much as you do. Thank you so much for watching. Stay safe out there, and we will see you in the very next story.